My name is Melanie Brady, and on behalf of SHARE Headquarters, I would like to thank you for joining us today. SHARE is pleased to continue our webinar programming with this informative and educational event. Please note that presentation slides and recording will be available post-webcast at www.share.org. Today's presenter is John Baker. John has over 20 years in the IT industry as both a customer and consultant, including 15 years specializing in mainframe performance at a large international bank and 6 years in enterprise I/O performance with IntelliMagic. As a customer, John designed, implemented, and maintained many critical projects such as WLM, goal mode, GDPS, data mirroring, and merging data centers. He has extensive experience with many performance analysis tools and techniques at the hardware, OS, and application levels. As a consultant, John has assisted many of the world's largest data centers with their ZOS performance challenges and held subject area chair positions with CMG for both storage and capacity planning for several years and is managing the System Z track for CMG 2016. John has hosted many sessions at CMG, SHARE, and IBM conferences, as well as several regional user groups. John is the Principal Z Performance Specialist at MBS Solutions, the creators of ThroughPut Manager, the leader in batch automation. We encourage you to submit questions throughout the event via the Q&A box on your webinar toolbar. These will be addressed at the very end of the presentation. I would like to now turn the web over to today's presenter. Please go ahead, John.
Thanks, Melanie, and thanks everyone for joining. Thank you for that very lofty introduction. The short title, you could just refer to me as Performance Guy, but thank you for those kind words. Short, simple agenda today. What I really want to talk about is utilization, title being Practical Considerations of Key Performance Area. Why is my system so slow? We'll talk about the actual definition of utilization and some aspects about it. It's a pretty broad term. We'll look specifically at PRISM, processor weights, and Hiperdispatch within the Z architecture, the hardware and the operating system. An overview of those and some of the implications. We'll talk about processor cache, very popular subject these days. If you haven't seen some of my previous sessions on that, what's in your nest, a lot of people talking about that. It's a pretty big deal. And finally touch on some of the other components within your system. I know we tend to focus mostly on CPU capacity, but there are a lot of components that go into making your system slow or fast. And finally, at the bottom here, keep your eye out for what I'm calling low-hanging fruit. Familiar with the term, I'm sure. I've got a few of these marked throughout the slides just to give you a few simple tips of things you can do. So now this is the total honest part. My colleague the other day said, hey, you know, why don't you just take a picture of your whiteboard, because this is the actual presentation as it came out of my brain several weeks ago, what you might call a brain dump. This is what I want to talk about. So some of you might get a laugh about that, but just a little bit of honesty. So utilization. This is going to be a core area of what we're talking about today. So I figured, like most people, well, let's start by Googling this and see what it means. And it surprised me what came up. These are the two first things that I see. Interesting that they primarily seem to refer to equipment and tool rental companies, but never mind that. What caught my eye was the point that utilization is the primary method by which asset performance is measured and business success determined, to put to use, to turn to profitable account. Okay, so utilization to use something, we know that, just intuitively we know that, but this comment about measuring performance and business success got me thinking, gee, if this might explain a lot why within the data center, within businesses, we have kind of this ongoing battle, if you will, between what I might call the finance and the techies, money versus performance. Because if you're thinking about utilization as a primary measurement of business success, then you might consider that, well, if you're running $1 billion company and your machines are running at 99%, you might interpret that as saying, well, that means I got 1% left on the table. 1% of $1 billion company, well, that's $10 million. That's real money. That'll get anybody's attention. I'm not sure that it's necessarily helpful to view it that way when we talk about computers, and I'm talking about mainframes, but this applies to any computers. This is what I'm talking about. Many of you might be familiar with this pattern. This is really just a basic queuing model, nothing special about it. And it's not the actual values that are important, but rather the pattern. What I've done here is simply set an arbitrary response or elapsed time of 1. That can be 1 second, 1 millisecond, 1 hour, 1 day, 1 year, it doesn't matter. The point is you're setting what your execution time will be for your transaction, your job, whatever, your unit of work at 0% utilization, and then projecting what happens to the total elapsed time as utilization rises. And as you can see, utilization rises exponentially, not linearly. So you can, when you're at very low levels of utilization, you can go up by 10, 20% and be just fine. When you get it to very high levels of utilization, you increase by another 10 or 20%. You go right off the cliff. You stop, essentially. To be clear with the actual values, and I'm not a mathematician here, but mathematically speaking, at 100% on the chart here, it appears that the line ends, but it actually continues on infinitely. And we can think about this in real life. All this is this is like Costco on a Saturday afternoon, if you've experienced that. The time once you get up to the front of the checkout would be your normal execution time, and that'll be reasonably fixed. These are experienced checkout people, and they've got electronic scanners, and they might get you in and out typically in a few minutes. The wait time, it depends how many people are ahead of you. This is where the utilization comes from. So the total time that you're in the store is primarily a function of how many people are in the store. And high utilization, there's a lot of people. So the point I'm making here, I guess, to counter the 99% argument that there's $10 million left on the table is that there's actually already significant waste that if you start equating these percentages to the investment you've put in your infrastructure in a percentage number, a lot of this is already wasted when you get to very, very high levels of utilization, and it's counterproductive to try and run even higher. So let's look specifically at CPU utilization. Now this simply refers to usage again, but more specifically the amount of work handled by a CPU in a given period of time, the first point here. These CPUs at their most basic level, and I'm not a electronics expert either, but I know enough about these things to make the point, that they're a series of switches internally, and they're simply on or off. So taken at a very basic level, if you were to actually measure a CPU at extreme intervals, nanoseconds, it's either 100% or 0. There's really no such thing as in between for the actual usage of a CPU. So when we're measuring utilization, what we're looking at is an average across time. And that time can vary, which can make the number vary greatly. If you're taking a look at the utilization of a highway, that is, you want to measure how many cars are on the highway at any given time using Little's Law, then you can calculate what the service time would be. Well, what is the frequency that you're looking at the highway? If you stand over top of an overpass and look down and take a picture every second, every 5 minutes, every hour, every week, every year, the time will vary what the utilization will be. If you take a snapshot and there's nothing there at that given moment in time, you would derive a utilization of 0, even though a second later there might be a whole bunch of cars. Just making that point. The next point, average across multiple components. Of course, within a mainframe computer, you have more than one CPU. So you might measure the utilization of the machine at a certain number. But what that is the average of all of the CPUs. And then the CPUs themselves are averages. So really we're talking about averages of averages here, stretching. Finally, there's logical versus physical, and we'll touch on that a little bit more. Everything is virtualized nowadays. When you talk about your basic MVS utilization, you're talking about the logical utilization of an LPAR, the logical utilization of logical processors, which is not the same as the physical utilization. We'll talk about how those relate. So let's look at some of this utilization within utilization. Take, if you will, basic scenario 1. I've got a box, 2 CPUs in it. I've got one CPU dispatched for 900 seconds in a 900-second RMS interval. That is fairly common. This is a 15-minute interval. A lot of people do that. And if you were to look at that in your report, you would say that CPU is 100% busy. Simply means it was used every second out of the interval length. The second CPU in the same machine, I measure that as 50% busy. That is, it was dispatched for 450 seconds in the same time interval, in the same 900 seconds. Look at scenario 2. Let's say both the CPUs in the same machine are dispatched for 675 seconds each in the same 900-second RMF interval. Now in this case, each of those CPUs would then be measured as 75% busy. So what's the total? Well, the average utilization of both of these machines, if you were to simply look at that number, would be 75%. But would performance be equal? Within the machines, would the applications behave the same? Well, what can we say about some of these numbers? Looking at the first point, scenario 1, one of the CPUs is 100% busy. So if an application tries to dispatch on that CPU, it's going to wait a very, very, very long time. Apply the queuing chart that we saw a minute ago. Whereas if it runs on the other CPU, it's actually going to run just fine. That one's only 50% busy. It's got lots of space. But another point is, what is the distribution? When was the application trying to be dispatched? Take that 450 seconds that it was dispatched. Well, that's within a 900-second interval. Do I know when? You don't. You don't from this amount of data. You know that out of 900 seconds, the CPU was dispatched for half the time and available for the other half of the time. You don't know that that distribution was uniform. You don't know, for example, that it was the first 7.5 minutes that was busy and the second 7.5 busy it was completely idle. Or maybe it was on and off every minute or every second. You really have no idea. So to answer the question about performance there, it depends. It depends when the application tries to dispatch. Low-hanging fruit. Balance, balance, balance. This is a term that you will hear throughout this session and really applies to so many areas, not just CPUs, but within your entire infrastructure. You've got multiple LPARs, you've got multiple machines, you've got multiple CPUs, you've got multiple channels, storage devices, networks. I mean, it's really probably the best thing that you can do, the simplest action that you can take, is to ensure that all of these resources are balanced. We come across countless sites that struggle with this problem. They may have a vast amount of capacity on the floor, but you've got a machine that's very busy. You've got a machine that's not so busy. Workload on the busy machine is suffering, so you end up having to upgrade that when you do have capacity on the other machine, for example. The business isn't happy because they have to spend the money, and really there's a better way to do it by ensuring that you're balanced. Look at another simple example. This is my laptop the other day, just running a bunch of SAS and seeing what that looks like on the machine. Now, if I look at this measurement, it tells me that I'm 15% busy. Again, what does that mean? Well, in one sense, that means, well, I guess I've got 85% of my capacity left. I could be doing a whole lot more work. But look a little closer, the time considerations. For example, you can see the windows on the right that represent each of the cores and their activity over time. You can see many, many peaks and valleys, meaning that any given moment in time, the utilization was quite high. Other moments, the utilization was not high at all. So how consistent is this load? It's not consistent at all. And then the point about the components. I can see of the 8 cores here, 4 of them show some level of activity, 4 of them show none. Now I can tell you, because I'm familiar with my machine, there are actually only 4 physical cores on this. There are 4 logical cores, which are parked, a term that you might be familiar with. But this is just another way of looking at it, that you can't just rely simply on that 15% number. Low-hanging fruit, understand averages. Yes, we report things in averages, and it's the practical way to do things, but understand what they mean. This doesn't necessarily mean that I've got 85% of capacity left to run. So let's look now at logical versus physical. It's something called LPAR dispatch delay. We see this in Z-series machine. This is probably the most common delay that I'm finding these days, and we look at an awful lot of RMF data from sites small and large all over the world, and really seeing this a lot. And what this is, it says here, this is a ratio of the logical processor busy to physical processor busy. Some of this, I think, is simply a natural human reaction to configure more logical processors, for example, to an LPAR, to ensure that it has access to the whole machine when it can get it. But if this isn't matching up with the physical capacity, you can see these types of delays. This is related to the overall configuration. So just mentioned how many LPARs, how many logical and physical processors. The CPU weights, these are critical. We'll talk about those some more in a minute. And the overall utilization. Now this isn't obvious, but it's very, very common, and I have to shout out and credit to Kathy Walsh. Many of you will know Kathy, one of the greats certainly in this industry, and she first talked about this way back in 2004, the link there to her web doc. This was specifically talking about delays experienced with CICS transactions at the time. This was even prior to Hiperdispatch, another thing we'll talk about. But this could really apply to any application. Also, just point out the variable at the bottom. I know a lot of your MXG users, this is something that Barry has created for us, just a variable to tell you what that delay percentage is. So let's see what it looks like. This is a data sample where we see this type of delay. Again, quite common. I've got a chart here, a period of time, number of variables involved, what the blue bars are. These are the number of active initiators or concurrent jobs, if you will. You can see how those peak up to 60 or 70, and then they've got some valleys. And then the green and red lines, the green is your simple MVS utilization. Measured value, straight out of your SMF70 record. All of this data is actually out of the SMF70. And the red value, marked CPU busy, this is the effective CPU. So where the green value represents the demand of the LPAR, what the applications within the LPAR are demanding in order to serve these applications. The red line is the effective CPU, that is the utilization of the physical cores that are serving this LPAR. Now, when they overlap, which they do a lot during the lower periods, that simply means supply is meeting demand. And this is a good thing, and you're healthy and happy. Where you see these gaps, particularly the one area that I've noted here, the 40%, that means that here I see the demand at 100%. The MVS busy is 100%, and yet the supply from the machine is only at 60. This can mean the machine is simply flat out. The other LPARs are taking their share, and this is as much as this LPAR can get based on its weight. Now, what do I do about this? Well, if it really needs this capacity, then I need to increase the weight. But we need to think about this in relative terms. If you've got multiple LPARs on the machine, as it looks like you would in this case, you can't just increase everything. We've talked about this in other sessions. We can't just continue to increase priorities and increase weights, because these things are all relative. If you've got a machine at 100% and you're going to increase a weight on one LPAR, that means you're going to reduce capacity on others. Getting back to balance, as I talked about earlier. Now, here's a benchmark. Some of you might have seen this one before in some of our other sessions. Yes, it's using Throughput Manager, but really it's just to make a simple point about utilization and about considering the performance to moderate what I would say the load. In a nutshell, what we've done in this benchmark is take an isolated machine, isolated LPAR, submit 1,000 jobs through a scheduler, steady state of submission, a mix of jobs, CPU bound, IO bound, some long, some short, nice big mix, all in the same service class. And first run them with WLM and inits completely unconstrained. And what happens, what we observe, is that WLM starts up to 300. Now, the number may vary. Again, here what we're looking at is the contrast. You can have a different capacity machine and see different numbers. But the point is that WLM will continue to start initiators in response to queue delay. See, as I'm waiting for an initiator, I can start more. WLM will tend to want to reduce delays that it can control. And queue delay is something it can control because it can start more initiators, so it does. The problem is when you get a flood of work like this, quickly you get up to 100% utilization. Now you have a large number of concurrent address spaces in your system, and they're all running at the same priority, which means WLM is now thrashing, trying to serve them all because they're at the same priority. He's essentially going to be giving small time slices to each job, but none of them are really getting done. So they're in flight, if you will, for a very, very long time. And you can see as the pink line drops onto the right, it takes about 10 hours to finish this. Then we reset, we start again, we run the jobs again with Throughput Manager. Now in a nutshell, what we're doing here, this component that I'm focused on, it's an automation component within Throughput Manager that wakes up every 10 seconds. And besides just looking at the utilization, it's also looking at the performance of the service class. It's looking at the CPU delays. And it's making a decision based on all these criteria about exactly how much work to run. The goal being that I want to get close to 100%, but I don't want that queuing chart where my wait time goes off the charts. I want to fill the highway without packing it until everybody's stopped. And using this method, as you can see, in this capacity with this load, it makes the decision to run approximately 25 initiators. It finishes about an hour sooner. And moreover, the green line is showing the number of jobs that were completed by Throughput Manager ahead of the other method. Because you want to get things out of your system. This is another area that we touch on when we talk about processor cache, things like that. Concurrency matters. Your system, WLM, the hardware will try and serve all of the concurrent address spaces that are in there. It will try and honor the priorities that they're given. But if you ask it to do too much, it's just going to thrash. Low-hanging fruit. I know this sounds oversimplified, but don't over-initiate. That doesn't mean run 25 initiators. It doesn't mean run 300 either. It means it depends on your capacity, your load, the nature of your workload. Obviously, I would recommend automation, but the point to be made here is that you want to load based on the utilization and based on the CPU delays and the performance of your workload. So it can't be a static number because these things will change over time, and you want to moderate that load. You can't force the issue by just starting more jobs and hoping they'll get done sooner. They'll actually take longer, as will all the other work in the system. Let's switch gears a little bit and talk about the hardware. PRISM, you've heard the term, I'm sure many of you. Processor Resource Systems Manager. It's a hypervisor for Z hardware. What's a hypervisor? Hypervisor is just a virtualization component. We have virtualization components in virtually every platform. PRISM is the standard for the Z hardware. Allows sharing of resources. Allows you to have multiple LPARs on the machine and share physical cores, share memories, share channels using MIF. allocates these physical resources to logical partitions, and you can have some preference using weights. We'll talk about CPU weights. So let's take a look, very basic look inside the box, if you will. Here I've got a machine with 7 LPARs, and I have CPU weights applied to each of these LPARs, 350, 100, 200, and so on. And I have a number of logical processors, that's LCPs, that I've decided to assign to each LPAR. The total weight in this case adds up to 1,000. That's not required, but that's common. We've got PRISM in the middle, and at the bottom we've got the physical layer. So I've got 15 total physical processors. Now, what observations can we make about this? Well, I've got 25 logical processors competing for 15 physical processors. So I have more logicals than I do physicals. This is quite common. The question is, how far do you go? Well, that's a giant depends answer. But the idea being that it would not be possible to have all 25 of these logical processors busy at the same time. It simply won't work. And if you try, you will see that logical processor queuing delay that we saw in the previous chart. So this is where the weights really get enforced. Weights only really get enforced when the machine gets to 100% or gets close to 100%. Prior to that, of course, you are allowed to exceed your weight if the other LPARs don't require their full weight. Also, I should point out the logical processors will limit the total capacity that you can get. So one of the rule of thumbs I would recommend is that make sure you do configure enough logical processors to be able to achieve your weight. Talk about what that looks like in a minute. But low-hanging fruit, consolidate LPARs. So when I look at this simple example, I've got what's probably my big production LPAR with a weight of 350 and 7 logical processors, LPAR 1, probably not doing much with that. But I've got 1, 2, 3, 4 LPARs, each with a weight of 100, each with 3 logical processors. Now, I understand that we may have business requirements for different LPARs, and we have test and development and acceptance and all these things. But from a strictly performance point of view, as much as you can lower your level of virtualization, and here I'm talking about LPARs, but any part of any component of virtualization would apply. If you can reduce that, you can reduce this ratio, your logical to physical ratio, you're going to improve your performance. There is overhead simply with creating and dispatching an LPAR, even if it's not very active. There is overhead associated with that. In this case, I've got 4 LPARs collectively with 12 logical processors. It would be far more efficient if I could combine those into, say, 2. And I probably wouldn't need 12 logical processors in total. It's doubtful that all these applications would be active at the same time, and you're going to save a lot of overhead there. So now we're getting a little colorful. Let's break down this share. The weights, as I mentioned earlier, that add up to 1,000 in this case, that makes it very easy to calculate the percentage. So what I have for each of these LPARs is I've got 35, 10, 10, 20% share, and you can see that illustrated in the chart on the right. So what does this mean in simple terms? And here I'm really talking about a pre-Hiperdispatch world. Effectively, the 35% means you have 35% of what I'll call the CPU pool, 35% of the 15 physical CPs illustrated at the bottom of the box there. Now, with a non-Hiperdispatch world, you have access to all of those. Well, in our case, LPAR 1 has 7 logical processors, so access to 7 at any given time. But it can be any 7. And they'll tend to run it at similar utilization. You can be dispatched anywhere, and this has worked well for years. But there is a better way. I'm going to get to that in a minute. Mentioned some of the rules already. Your weight, just to be clear, this is your guaranteed minimum. This is not a maximum. Your maximum is going to be the limit of your logical processors. Essentially, if I've got 7, I can run 7 at 100%. In theory, I can run 7 physical cores at 100%, or in this case, that would be close to half of the box, 7 out of 15. So LPAR 1 has a theoretical capacity of up to 50% of the box. But its guaranteed minimum is 35. So that means if all of the other LPARs are taking their share, it will always be guaranteed a minimum of 35%. Low-hanging fruit. Pointed this out already, but just to be clear. Ensure that you have enough logical processors to achieve your weight. And by that I mean, if I take this 35% share, that's going to work out to, about 5 or so CPs. Well, if I only configured, say, 3 logical processors, as I do have on some of the smaller LPARs, I would be unable to achieve that weight. I would only be able to access 3 out of the 15 physical CPs in the pool, which is less than 35%. PRISM will accept it. You can enter that number, but you would be, as we say, shooting yourself in the foot. So let's bring things up to speed a little more current. Hiperdispatch, which is the way that we run today. It's not required. I think I've seen one site in the last little while that's not running Hiperdispatch, but it's quite common. It's been the default for a few years now as of ZOS 113. You do have the option to turn it off, but it's default on. Now, what Hiperdispatch is all about, this is a method of what we'll call aligning your physical CPUs with your LPARs, and indeed even with the logical CPUs. The goal is to take advantage of newer hardware design, and I'll talk about what that means as well in a moment, this newer hardware design. This also reduces multiprocessing overhead, or something you've probably heard over the years, the MP effect. The MP effect is simply when you have multiple processors, hence the term multiprocessing, servicing a workload. Within a machine, if you have a single, we call that a uniprocessor. As soon as you have 2, 3, 10, 20, now you're multiprocessing. The more physical cores or processors that you add to a machine, the more inherent overhead you will incur. That is what's called the MP effect. That overhead is due to a number of factors, but primarily it's due to integrity. Of course, the system has to maintain integrity of the shared storage. So, and by storage I mean memory, I'm not talking about disk. And if a given CPU wants to update an area of shared memory, it has to ensure that the other CPUs are not updating that same area of memory. So there needs to be communication, and that incurs overhead. And again, the more you have, the more overhead you have. Just a quick rundown comparison. Hiperdispatch, you may have heard the term vertical alignment versus horizontal. We'll be more specific about that. Your percentage share without Hiperdispatch is distributed across all available physical CPUs, as I discussed in the previous example. With Hiperdispatch, your share is distributed by physical CPUs. Without, it's distributed across all LPARs, all CPUs distributed across all LPARs. With Hiperdispatch, your logical processors become marked vertically. You've heard the terms vertical high, vertical medium, vertical low, sometimes short form as VH, VM, VL. Also, just an observation, the utilization of the CPUs tends to be even without Hiperdispatch because, of course, I can run anywhere. Any LPAR, any logical processor can run anywhere, so we'll use them all. Whereas with Hiperdispatch, unused or vertical low CPUs tend to be parked. Vertical highs tend to be busy. Vertical mediums tend to be low. And that might seem counterintuitive when we think about utilization. Why would I run one CP hot when I'm not running the other at all? Well, hot is a relative term, but also there are some advantages to keeping the work on fewer processors. We will talk about why. Cool, graphic. Okay, let's talk about vertical alignment. This is our same box from before. Let's look at LPAR 1. This was our production LPAR with weight of 350, 35% of the machine. So how do we calculate this? Quite simple. You can figure out exactly what you're going to get with some basic back of the envelope math. with Hiperdispatch, 35% share. I've got 15 physical cores in the machine, physical CPUs, 35.35 times 15 is 5.25 CPs. So first thing I can say out of the gate is, okay, that's what I'm going to get. Now, how does that break down? Now, there's a couple little rules here. I've got an asterisk beside this, which I'll point you to the link at the bottom of the page and talk about that exception in a moment. But essentially, 1.0 is a full processor, or what we'll call a vertical high. Between 0.5 and 0.99, that's less than a full whole processor. We call that a vertical medium, and less than 0.5 or 0.49 and lower, you're going to get a vertical low. How does this break down in this example? Well, the first rule is that every LPAR receives at least one vertical medium, and this will cost you 0.5 CPs out of our 5.25 total allocation. So I take my 5.25, I subtract 0.5. I've got one vertical medium allocated so far, and I've got 4.75 left. Now that 4.75, I can see, well, I've got 4 whole CPs in that, so I'm going to get 4 vertical highs out of that, and I've got 0.75 left. So far I've got 1 medium, 4 vertical highs. Out of that 0.75, I've got another 0.5 I can get out of that. That's another vertical medium. So now I've got 2 vertical mediums. Finally, I've got 0.25 left. That will be a vertical low, and this will be my total. 4 vertical highs, 2 vertical mediums, 1 vertical low. If you configure with this number, you should be able to check the hardware. You can actually see this from the Type 70 records. It'll tell you what your allocation was, and that's what you should expect. Now, the areas I just circled to point out, and this is another aspect of this, we're going to dive a little further into, but the alignment is to specific processors. So vertical high doesn't just mean any 4. I'm going to specifically get a given 4. Now, you might have heard the term dedicated or semi-dedicated. These are semi-dedicated. This is not the same as an actual dedicated processor. You can do that. You can still dedicate processors. But if you don't, and it's common that you don't, these can still be used by other LPARs, but only if this LPAR absolutely doesn't want them at all. And I wouldn't expect that if you're matching your weights to the expected demand of the applications. Finally, just to point out the link at the bottom related to the asterisks at the top, there was an update in the spring that's specific to the Z13. I'd encourage you to check into that. If you have a Z13 and you have some very small LPARs, there's an exception to the rule here. And in a nutshell, what I will say is if you have a calculation of less than 2 for a very small LPAR, the normal math would say, well, I'm going to get a vertical high and a vertical medium out of that. The problem that they were seeing in the Z13 is it is possible that that vertical high could be on one node and the vertical medium be on another node, and then the overhead is actually worse because they are not sharing a lot of the same processor cache further up the tree. So a decision was made to change that, and the result is that you will get 2 vertical mediums rather than a high and a medium, and they will be on the same node. Now, this is what that looks like. I know things are getting a little bit busier, but you might have seen the picture on the right before. This is in common in many of the IBM manuals and red books, and it's showing the basic physical layout of the Z13. This is not all that different from previous generations. In fact, this architecture started with the Z10. And the point that we're making here is, as I said, those 4 vertical highs will be specifically allocated, directed to 4 physical cores and within the same node. And as you can see, the advantage of that when you get into processor cache is that when I get dispatched on the same core with the same applications, which is probable from the same LPAR, that I have a much better chance of a cache hit. And by cache hits, I'm talking specifically within the processor cache. The level 1 and level 2 are physically on the cores. So I want to dispatch on the same cores I did last time, hope my data's there. Even if it's not, it's going to very likely be in the local level 3 cache, which there's one of those for every set of 8 cores. This is the main idea behind this. Now, PRISM does this for you. You don't have to do this. You just configure your LPARs as normal. It will naturally align these things. It's my understanding that it will even move them if you make a configuration change. PRISM may actually move the allocation of your processors to other physical cores to keep them together within the same drawers, within the same nodes, and within the same processors. Low-hanging fruit, I would hope it's obvious. Obviously, you want to maximize your vertical highs. You want to have as many semi-dedicated processors as you can to improve your chances of cache hits and avoid the vertical lows as much as possible. If you have a lot of those, that means you could be anywhere. You could be dispatched on any core that gets unparked at any time. Very likely that the data that you want is not going to be in cache there. So speaking of cache, switch gears a little bit to that. One of the reasons that the focus is on cache now, processor cache, is basic performance. CPUs, of course, have continued to increase in speed dramatically. Z13's got a 5 gigahertz processor, 5 billion instructions per second. The caches got very large. You may have heard about the 10 terabytes of memory that you can have in this box, but it's not as fast. You can access the memory as quickly as the processor can execute instructions. And this gets down to some of these things that you might hear about of cycles per instruction. You know, how many cycles does a processor have to wait for an instruction to be fetched if it's not in the local level 1 or level 2 cache and it has to go further up the chain. And we're talking about several miles of copper wire within this infrastructure. So if you can imagine the distance, yes, it's at the speed of light, but we're also talking about a processor that can do 5 billion instructions per second. So consider it not so much as absolute time lost, but in number of wasted cycles lost in a cache miss. Or put in simpler terms, I've used this history before, so I found it helpful, the memory parking loss. There's you, and there's your car. Your car being, in this case, in the CPU analogy, your next instruction or the next piece of data that you need. As fast as that processor might be, if that instruction is all the way up in memory, that's going to take a lot of cycles, potentially hundreds of cycles to actually fetch that, during which time the CPU is spinning away unproductively. You've probably also heard the term relative nest intensity, or RNI. This is a simple number measurement. It's not the end-all be-all, but it's certainly one of the numbers that you should be looking at, referring specifically to data out of your Type 113 records. This is the CPU measurement facility that gives you the specific statistics from the processor cache. What are the actual hit ratios, miss ratios on each of the levels, level 1, level 2, level 3, and so on. There's a lot of very good data in there. You could certainly get lost in the weeds, but even if you're just looking at a very basic level of cycles per instruction, how many cycles is it costing me to do each instruction? You start seeing very, very high numbers. This is a sign of a problem with your performance, either your utilization at some level, talk about utilization, but it's something you want to look at. Become familiar with your workloads as well. What is typical? It will look different on different LPARs with different workloads. It will certainly look different based on your Hiperdispatch configuration. Vertical highs will have a much better looking relative nest intensity than vertical mediums and vertical lows, respectively. A point I'll make about this, and shout out to my buddy Scott Chapman. He works with Peter Enrico now, and he's done this presentation a few times. He calls more slower versus fewer faster. And it's something to think about. And in a nutshell, what Scott's saying is, say, for example, you have a configuration, older machine with maybe 10 engines in it, you haven't upgraded for a few generations, you just look at the total MIPS, total capacity that you need, and say, well, we only need this Z13 with 4 cores. That's got the same capacity because the engines are so much faster, the performance is so much better. Well, it may have the same total capacity, but you've gone from 10 engines down to 4. And think about this just in the cache perspective, looking at the diagram here. Each core has a dedicated level 1 and level 2 cache. So I went from 10 level 1 and level 2 caches down to 4. So my concurrency is going to be diminished significantly. What Scott is suggesting is that you consider some of the subcapacity options. Maybe instead of a 704, you're looking at a 606 or a 508. The actual clock speed of those engines may be slightly slower, but really that's only going to be noticed if your applications require an extreme level of performance. And this gets down to measuring the transaction CPU times, because that's really what's going to be most sensitive to this. Batch will probably be just fine. But it's worth looking at. It's worth exploring. It's a deeper subject. I don't really have time to get into it today, but look that up, or certainly ask me. I have all these papers and happy to share them with you. Finally, just touch on a couple of other areas here. What's a miss versus a miss? I've already talked about cache misses within the CPU, within the local CPU caches. Well, I can have a miss that has me go out to auxiliary storage, paging. Does anybody page anymore? I thought it was gone, but occasionally I still see disk-based paging. Given 10 terabytes that you can get in a Z13, it does seem unnecessary. But if you do some of that, these Flash Express cards look very, very good, or what IBM is now calling storage class memory. Certainly a better alternative than disk. Obviously, it's essentially solid-state disk is what it is, but it's within the machine. So you're not even going down to the I/O subsystem. You're not going out a channel. You don't have to interface with the controller and then get down to a disk drive, even if it's a flash drive. It's going to be infinitely better to use these. I'm not sure about this price point, but it certainly seems like a very, very good idea. Utilization of channels, for example. I'm not sure how often people will look at these, but if you consider that your overall system isn't just processing instructions, it's got to read and write data all the time. And ultimately, as big as memories might be, it's got to come from external storage, which means it's going to go out channels. Are you looking at your channel utilization? Probably something we used to look at, but now we've got blazing fast FICON, and we've got Z high performance FICON. It might be a thing of the past, but it's worth looking at. Particularly, I'll point out here, MIF and balance. We used to call it eMIF, and then, of course, SCON went away, so now it's just MIF. If you've got a very big box with a lot of LPARs on it, what you probably have is a lot of logical channels on these LPARs sharing the same physical channel. So same concept of virtualization. You want to see, am I actually driving the hardware too hard? And balance. You're obviously going to have multiple channels going out to your storage infrastructure. Are some busier than others? Is there ways to rebalance that workload rather than having to buy faster hardware? Taking it further out beyond the channel to the FICON director. Guys like Steve Gundert will talk about this. Lots of good information from Steve at Brocade. Again, if you want some more detail, happy to pass that your way. But in a nutshell, what I'll point out here is that you want to verify simple things such as your data rate. So you might have a 8 gig FICON channel. Well, do you have an 8 gig port on the director? Does it only support 4? Does it support 16? And the other end only supports 8. This is just basic network rules. It'll work, but it's going to auto-negotiate down to the lowest speed. So actually check what you're getting and make sure that your hardware is capable of these types of things. There's also very good statistics, even reported back up to RMF on the FICON directors. These are 74.7 records. They will tell you if you're having any port busy activity, errors, things like that. You really shouldn't see with modern hardware, but something to keep an eye out for. Finally, you get down to the storage controller itself. Well, I mean, these things are computers unto themselves now. A storage controller has many, many processors of its own. It's got front-end cards with processors and bus and channels within it. It's got central processors within the machine. They have large caches. And the back end, they have drives. And more, of course, we're seeing flash. Looks like the 15K RPM drives are probably going to go away. We're seeing a lot of flash. Seeing even all-flash storage, very, very popular. Certainly one way of what I would say throwing hardware at a problem. Very, very fast, no doubt about it. I guess what I might just say is if you're doing that, are you masking a problem that may come back to bite you later? I would say you should be doing the similar level of capacity planning with your storage controllers as you are with your CPUs. They have capacity. You don't just want to look at dollars per gigabyte. If we only look at dollars per gigabyte, we just buy tape and go home. But it doesn't work that way. You want to actually see what kind of performance you're getting, and some of the points I'm talking about here, front end and back end of these machines, measuring these utilization numbers. Now finally, where's the data? I know I'm running a little late here, but just as a quick reference for you, some of the areas we've touched on, where do I get all this stuff from? CPU utilization, of course, the ever-popular Type 70. There's a wealth of information in there. You should be collecting this on every LPAR. We'll give you all of the logical and physical utilization, also give you PRISM information. You can check on uncaptured time, for example, things like that. Hyperdispatch, a couple of subtypes of the 99. Some of you will probably recall in the old days we never wanted to keep the 99s turned on, primarily because of the workload manager records can be quite huge. You can certainly turn on these subtypes if you haven't already. They are not so huge, and they are very, very useful because they will give you that information we're talking about with alignment. They will tell you where your LPARs and where your logical processors are being aligned. Are they going to the nodes that you want them to? Are they being self-contained as they should be, and so on. Type 113, the CPU measurement facility. If you're not collecting this, I believe Kathy Walsh will have you on her hit list. It's really, really critical. I can't say enough about it. If you call IBM for help, they will ask for this. If you don't have it, they may very well say we can't help you. Simply with the hardware today, the Type 70 is not enough to tell you what's really going on within the infrastructure. You've got to have these records turned on. ZDC, I didn't touch on those, but if you're using the enterprise data compression cards, these are very, very popular. Seeing a lot of good results in the performance of these cards. And there is a record type that's come out now, another subset of the 74. Seems we just put everything in the 74 these days. But it will tell you the utilization and throughput of that card. Of course, good old-fashioned auxiliary storage paging. 71 will tell you how much stuff is in your paging packs. Hopefully they're empty. And 75 will tell you the performance of those. Flash Express, also new, another subtype for the 74. I believe this just comes out in 2.2, but very nice, giving you some statistics. If you're using that storage class memory within your machine channel, the old 73s should have those on. FICON Director, you do have to enable the cup feature if you're not doing this within your FICON Director, but these are those stats I mentioned earlier, giving you any errors on the ports or buffer overruns, things like that are in those records. And finally, all kinds of stuff on storage. The old 74.1 for each logical volume, 74.5 for the cache, 74.8. Very important if you don't have this on. It's what gives you port statistics and extent pool and rank statistics within the controllers. All the modern controllers, IBM, Hitachi, EMC, they all report those statistics back to RMF if you have this option turned on. 78 for LCU, 42 for dataset. That should cover it. My goodness, I went long. Thank you for hanging in there. I know that was a lot of information. Certainly open to questions now. If anybody has any, I've not been monitoring the chat box, but feel free. I'll pass it back to Melanie.
Great, thanks so much, John. The first question that we had is, what is a reasonable RMF interval length, and do I need to collect these records on all systems?
A reasonable RMF interval length. Well, of course, universal rule, it depends. The interval length is more just about what level of granularity you want to see. This is, of course, what we call post-processed data, so it's not the same as an online monitor. I've seen interval lengths of 1 minute. I've seen them at an hour. Probably the most common is 15 minutes. I think that's just fine. There's not any significant overhead with increasing the interval length. That's more attributed to the cycle time, and that's something else. But it will collect a lot more data if you have a higher interval length. So if you're running SAS, MXG, things like that, that will run a lot longer if you've got a short interval length. And all of the records, good question. Let me quickly just jump back here, refresh my memory. A couple of them for sure. The FICON Director, you only need that on one LPAR. 74.5 cache stats, only need that on one LPAR. I think the others you probably need on every one.
Excellent, thank you. Our next question, do you have a good ratio for logical to physical processors?
A good ratio for logical to physical processors. Well, obviously, ideal would be 1-to-1. You know, that would be the perfect scenario, but that's not realistic with multiple LPARs and so on. 2-to-1 is quite common. So in the previous example, we had 15 physical processors. You could have up to 30 logical spread across. That's pretty reasonable. I think when you start getting up to 3-to-1 and higher, that's when you're going to really start to suffer. That would be my rule of thumb on that.
Great, thank you. And one last question. A Z13 can have 150 CPUs. Is there such a thing as too many?
Well, if you think about it, yes, the theoretical capacity is really quite staggering, and with apologies to the marketing folks, it must be really fun to be able to talk about these, because if you do some of the math, you can have up to 85 LPARs, if you think about it, 85 LPARs on a machine. And each LPAR, in theory, could have 150 logical processors. And then you could configure 150 physical processors on the machine. So what does that work out to? That's 22,000 you know, levels of virtualization, if you want to look at it that way. That's crazy. That's my short answer. That would be crazy. But is there an absolute number? What I do see as a general guideline, I've heard this from Kathy as well as others at IBM, generally when you get up to over around 30 physical cores on a machine, at that point the MP effect is starting to degrade performance to such a degree that it's worth it getting another machine. Obviously the architecture allows you to go further, but that'd be my guideline. I have no reason to disagree with IBM on that.
Wonderful, thank you. Any concluding thoughts before we wrap up?
Just balance, 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 balance. Know your workload, know your hardware.
Perfect, thank you. And that concludes today's webcast. We'd like to thank everyone, especially John and the MVS Solutions team, for attending the event today. This feature will soon be available on the SHARE website at www.share.org. There is a survey after this webinar for you to complete. We thank you in advance for your feedback. Thanks again for joining us, and have a great day.